I can't believe this. You never said that.
For 3 days. 3 days.
Reset always depends on what.
Then you might go.
Always reset.
Hello, everyone online. Can you hear me? Someone put something in chat. Can you hear me? Bye.
No, I can.
Oh, yeah. Yeah. Okay, cool. Okay. Over engineered, buddy.
Like high school, I think bowling and like I don't know, golf down. So, is it recording?
I think we're recording.
Yes, it was recorded.
Okay. So online, you can hear me, right? Yes, can hear. Can you see my screen? Other thing online? I go up and down. Are we all able to see this? Okay. Okay, right, we'll get started now. Thank you everybody for your patience. Apologies about that. So yeah, welcome to the ELEC Core 1 crash course run by myself and ELSOC. My name is Hugo Sylvester. You might have got an email about them awards, just saying, just keep that in mind. Anyway, the fly there. Okay, so for today, I've been given some questions from Felipe and from Hua, who you might know, might not know. He's one of the senior academics, which is meant to be quite representative of the final. He hasn't given me a paper though, just been a selection of questions. So the length of the question, like this might be too many questions for your final two that I'm not sure. Look at the other finals. But these are relevant questions. So yeah, firstly, yeah, thank you to Felipe for that, because it's pretty unusual to actually get questions that are probably relevant. Usually you have to kind of guess. I'll start by just showing you the questions I'm going to go through, and then yeah, I'll just go through them. So here's our first question. Apparently this is from 2017. Everyone can hear me if I damn right. Everyone can hear me? Yeah, cool. Yeah, calculate open circuit voltage, short circuit, yada, yada, yada. Pretty standard Thevenin question. The next one is going to be this question, which is a transient response. This is RL with a couple. So we'll go through that. Here is the first big op amp question. This is just DC op amps. We'll do that. This is kind of a derivation sort of question. We'll definitely do this one. This is quite typical. This is op amps plus phasor domain, which is a pretty easy question for them to write. So you'll probably get one, to be honest. What's next? These are the two questions. I probably won't do both of these. Or maybe I will do both of these. I'll try my best. The first one is a very standard just AC analysis question, just full on like find V0, right? So that's just going to be, yeah, nodal mesh or something. We've also got a DC source, another source. And the final question is very power oriented, which I probably definitely will do because I know power is the newest topic. Yeah, so I'll pretty much work through from start to finish. Let's get into it. So I'll just prepare myself this question. Slide. All right. I've also got my data sheet here. It's important you guys keep access to your sheet. I'm also going to try and scroll as little as I can because I'm aware that is not a good idea. Okay, here's the first question. Calculate the open circuit voltage and short circuit current at terminals A to B. So to do this, I'm just going to start by redrawing the entire circuit so that I can write on it more easily. We've got 21 volts. We've got 3 kilo ohms. We've got this kind of loop here. That is I0 going down like that. Then over here, we have this dependent source because it's a diamond like this. And I'm just not going to draw RL. 2K ohm, and we've got 20 I0. I'm not going to draw IL because it is a load resistor. I know it's a load resistor, firstly, because it's between the terminals A and B, and also because it's being called RL. That's a great sign it's a load resistor. So I'm just going to get rid of that for now. It's not so important. So I've been asked to calculate the voltage, open circuit voltage VOC. That is this voltage here. And also the short circuit current. The short circuit current would be, if I short these wires together, whatever current that is going to be the short circuit current. So this is this sort of like setup where you've got something on the left here and something on the right here, and they're not connected by a loop you can draw. Like I cannot draw a loop between these two. You'll notice I can only draw this line. You'll see this a lot because this is kind of what NPN transistors look like. Wow, exciting. It's so relevant. Anyway, point is, the observation you can make is that this stuff this stuff cannot really affect this stuff. The only reason they're related is because of this dependent source. So that means I can just find I0 directly. That's just going to be the current through the 3 kilo ohm resistor. So I'll just apply Ohm's law. I'll use I0 is equal to voltage divided by resistance, 21 over 3K. That happens to be, I think, it's 7 milliamps. I think it's 7 milliamps. Cool. And now for VOC, that is just the voltage across the 2 kilo ohm resistor. So that is just, again, Ohm's law because we've got a current source. VOC is going to be 20 I0 times 2K, which is 20 times 7 milliamps times 2000. I shouldn't write milliamps, sorry. 7M times 2K. That happens to be 280 volts. I short circuit will be similar, but even easier because you'll notice that as soon as we short circuit this, we actually short out the 2K resistor. So this is just the current from the current source. So I short circuit is equal to 20 I0, which is 20 times 70 milliamps, which is 140 milliamps. All happy with that? All good. Feel free to yell if there are questions. Online, I can't really see you, so good luck asking me questions, but try your best. I might look at it at one point. Actually, that would be nice. Sorry. Teams. Hopefully we've all got. Yeah. Cool. So that's, there you go, 4 marks in the bag. Fantastic. Part B, obtain the Norton equivalent circuit with respect to terminals A and B. So Norton equivalent, usually we like Thevenin equivalent. So if I just find the Norton equivalent, I'll probably start by finding the Thevenin equivalent and then source transforming. But we probably don't have to do that in this case because we've already calculated I short circuit. So since we already have I short circuit, we know that I short circuit is what's going to be the current for our Thevenin Norton equivalent circuit. So our Norton is just the short circuit current. So the only thing left to calculate is the Thevenin or Norton resistance. So if we were doing that, we'd think, oh, which method will I use, 1, 2, or 3? Because we've already found I short circuit, it probably makes sense to use method 2. So we happy with that move? Yeah. Using method 2, we would find I short circuit, which we've already found, and then we would write R Thevenin is equal to V Thevenin, or V open circuit, which is V Thevenin, divided by I short circuit. That's right, isn't it? P equals IR, R equals V on I. So I have to do that every time. So V open circuit divided by I short circuit happens to be, I've actually done the maths in advance this time rather than asking you guys to do it. I'm really prepared like that. It's 2 kilo ohms. So we can conclude that our Norton equivalent circuit is just that I short circuit, which was 140 milliamps. And then a 2 kilo ohm resistor like that. And we've still got the terminals A and B. Cool. Yes. Okay, C is determine the value of the load resistor for max power transfer and calculate the max power that can be delivered to RL. I will just note that this is actually given in your data sheet. If I just scroll up a little bit, you'll see that we've got max average power transfer and also maximum power transfer. Maximum average power transfer will refer to AC because AC average is a more important measure than maximum because things are changing, right? So an average makes sense to take. But in DC, we can just use these two formulas here. The RL is R Thevenin and the Pmax equals V squared on 4R Thevenin. And we can just apply those directly. So the first formula was RL equals R Thevenin. So that's great. We know R Thevenin. 10 milliseconds. Yeah, sorry. Okay, we know R Thevenin is the same for the Norton and the Thevenin circuit, so that's just going to be the 2 kilo ohms. My head was like, are they the same? They are the same. They are the same. That's how source transformation works, right? You keep the same resistor. It's only the source that changes. So that's great. We also actually have V Thevenin because V Thevenin is V open circuit, sorry. So that was one of the other things we calculated before. So we can reuse that result. That's 280 volts. So that's our max power point, 2 kilo ohms. And our Pmax is just going to be VTH squared over 4 Thevenin, which I just got from the formula sheet above, which is 280 squared divided by 4 times 2K, which happens to be, where's the number? 9.8 watts. Okay, so that was question 1. I'm going to make a couple of other points about question 1. The first thing I'm going to say is I reused a lot of results between part A and part B in question 1, which in general you cannot do for a Thevenin circuit. In general, your part 1 for a Thevenin circuit will have an open circuit at these nodes here, which often means you lose components. You'll often have components in series which have no current and therefore cannot drop voltage anymore. So you get rid of them. That will be a different circuit to if I short circuit these terminals here. In that case, the circuits are quite different and you can't necessarily reuse your results. In this case, we could reuse our results though, because that didn't happen to be the case. Does that kind of make, are we happy? Are we happy? How are we going? Yeah, I'll say it again. Let me give you a more concrete example. Let's say I had a circuit that looked like this. I don't know, it's got some random network of stuff. But critically, it's got this series resistance here between A and B. When I can calculate VThevenin, I know that this is open circuit. So I know there's no currents going through this loop. So when I do that analysis, I'll be like, okay, I don't need this resistor anymore. Goodbye. And I'll probably draw the circuit like this. And that will be VThevenin. So I'll get my VThevenin. Maybe along the way, I calculated some currents here. And the question is, if I'm now doing method 2 to find my RThevenin, let's say like this, R1, and I short circuit this, could I reuse that I1? And the answer is no, because the circuit is quite different. It's not the same at all. I have a different resistor. Yeah, my point is, in general, you cannot reuse results between finding VThevenin and finding RThevenin. We happy with that? I think that's just a common error. All right. Any other questions for this one? Otherwise, I'll move on. We'll get all. Sorry, what did you say? Sorry, could we just be quiet for a second? What did you just say? So why is RL the same as RTH? That is the max power transfer theorem. So for a Thevenin circuit, that's what it is. Yeah, that's the formula. Yeah. Yeah. You just treat it as a new circuit and do your normal techniques. My point is, some people, will go, oh, I already know I1, so I'll reuse the same number, but that will give you the wrong answer. Yeah.
Is it separately, or is it easier to do it the way that you've shown?
So I found I short circuit in the first question because they explicitly asked me to find I short circuit. If I was asked to find the Thevenin equivalent circuit, I probably wouldn't do that. I'd probably find VThevenin first, and then I would use whichever method I feel like to find RThevenin. And that could be method 2, in which case I would need I short circuit, but it might not be. It could be method 3, it could be method 1. Does that make sense? All right, cool. All right, sorry, I'm going to continue because I have already wasted a lot of time fucking with the projector, so here we are. All right, here's part 2, very classic RL transients. RL transients are the same as RC transients, except you care about currents instead of voltages. Like they have basically exactly the same formulas. All the transient, V infinity minus V0, same stuff, right? It's just currents. I'll reinforce this by going up to the formula sheet quickly. Sorry for scrolling all the time, but I'll go up to the formula sheet. You'll notice that these two formulas, this one and this one, have exactly the same shape, except this one's voltages, this one's currents. So that's the critical formula for this. First thing for these circuits is so for every transient, we're going to want to write some sort of I of t is equal to I infinity. I think it's plus I 0 minus I infinity. Wait, is that right? Have I done that backwards? Hang on. No, that's right. I 0 minus I infinity e to the minus. I'm going to write this out in full, t0 over tau. The task is always find I infinity, find I0, find tau. Then you're done. Those are the 3 unknowns in this formula. So I0 is always the point of doing these. Sorry, I0 and I infinity are meant to be in DC steady state. So they're either a long time before or a long time after some transient has occurred. So we'll do that now. So the first question is asking us find I0 of t for 0 is less than or equal to t is less than 4. So the first thing we have to think about is what does the circuit look like before t equals 0? The answer is, if I look at these switches, both of them are open because by the looks of it, this one closes at t equals 0 and this one closes at t equals 4. So before t equals 0, we have no switches open. Happy with that? I've just gotten that from the diagram. So I'm going to draw what that circuit looks like with all those switches open. The answer is it's pretty boring. We've got this resistor and that inductor, and then everything else is just open circuit. Because they're all open circuits, no currents flowing, I can conclude that I0 must be 0. I cannot draw a full loop, no currents. That's great. There's no I0. Next question is, what is I infinity? So critically, I infinity is not after both switches close. It's only after the first switch closes. Even though the second switch closes at time equals 4, for the purposes of writing this equation, I want to know what the effect of this transient is, just the one switch closing. So if we just shut that switch, we get this. And sorry, I'm flicking around a lot again. I'm going to have to do it more because I can't remember what the circuit looks like. We've got this 2 ohm, got another one over there, and the inductor. That was 40 volts, I think. 2, 8, 5 Henrys. Okay. Other thing to state, this is DC steady state, so I should actually replace my inductor with a short circuit. With a, oh, not like that. With a, I'm just going to write like this, with a short circuit, and that is my I infinity. So now this is just a series circuit, 1 voltage source, 2 resistors. I can just apply Ohm's law directly. I'm going to do that. I'm going to call it I infinity is equal to, so it's going to be V divided by R, so that's 40. 2 plus 8 is 10, 4 amps. Fantastic. The only, so now I've got I0, I've got I infinity. The only other thing to find is my time constants. Once again, recalling, if I go back to the data sheet again, we're given the time constants, I believe. We are. There it is. L divided by R. So R is just the R Thevenin as seen from the inductor terminals. So that could be, you can calculate that with any of your usual 3 methods. Looking at this circuit, oh, and the other thing to mention, sorry, it's R Thevenin from any of those terminals in the same circuit that you get with V infinity. So I want to consider this circuit. Yeah, I don't think I articulated that very well. My point is tau, like the R that the inductor sees, is the R it's discharging through. So you need to look at the circuit while it's discharging, which is this one, and go, okay, this is my circuit for which I'm going to calculate tau. So yeah, basically what I want to do is I want to find R Thevenin across the inductor terminals. I can use method 1 for this. We only have independent sources. If I whack off the independent source, I've just got this circuit, just 2 series resistors, 2 and 8. So I can conclude that R is just their sum. 2 plus 8 equals 10. Fantastic. So now tau is going to be, I think it was L on R, right? So it's going to be, it's 5 Henrys, I think. 5 over 10 equals 2. Now I've got everything I need. I can write I of t is equal to, I of 0 was 0. So it's going to be 0 minus, yeah, oh, whoops, backwards, sorry. 4 minus 0 minus 4, was it plus? Oh my God, plus. Okay. E to the minus, yeah. That's a good point. That's a good point. 5 over 10 is indeed a half, not 2. I'm going well. Look, I had something due this morning. Okay, so I was up all night. Chill out. Okay. Anyway, so we've got this T0 in here. T0 is the point at which the transient occurs. So for this one, it's going to be 0. So T0 is equal to 0. I kind of implicitly assumed that earlier as well when I wrote this I0. So anyway, point is our I of t for this region of time is going to be, I'm going to factorize out the 4s. 4 times 1 minus, no, what? Hang on, how do I factorize numbers? I'm not going to factorize it because I'm freaking out. 4 minus 4 e to the, damn, I'm really having a moment. Minus t divided by a half, which is the same as 4 times 1 minus e. There we go. Holy moly. Minus 2t. Okay, so that's going to be our first transient period. I moved kind of fast through that. Are we happy with that? I'm going to have to do it like again. So you're going to see it again. So maybe I'll do it again and then we'll ask questions. Because the next one is determine I of t for t is greater than 4. So this is the next transient period. So we're basically going to do this again. So once again, I'm going to write, okay, great. So I of t is equal to sum I of infinity plus I of t0 minus I of infinity e to the minus t over tau. T minus t0, sorry, I should actually do that over tau. Great, okay. So the observation I can make, firstly, is that I of t0 is going to be at 4 seconds. We can reuse our previous result this time. So we know that immediately before the switch, our inductor current has been following this equation. So to get I of t0, I can just substitute 4 into this formula. There's going to be 4, 1 minus e to the minus 2 times 4. This happens to be pretty much 4. You can just type that into your calculator. I think I get like 3.99. Yeah, I'm going to write that as 4. Cool. So then the question is, what is I infinity? I infinity. So as usual, as before, we want to consider, okay, what does this circuit look like a long time after this transient has happened? After this transient, both switches are shut, so we have a circuit that looks like this. I'm just copying this directly across. Nothing, I haven't done any magic just yet. Magic comes later. Actually, there's no magic. This is all just normal. Note the polarity of the voltage source. Often they'll like flip one over just to be like, oh, it's flipped over. You're going to be able to deal with that? The answer is yes, of course you're going to be able to deal with that because you're incredible at this. I infinity. Okay, so we want to find I infinity. I'm just going to do a mesh equation at this point. Like at this point, you could look at this and be like, oh, how should I do source transformation? Now just do mesh analysis. It's like it's too easy. There we go. There's I infinity. That's going to be I1. I just made that up, by the way, right? Just some random currents. I'm going to assign every resistor a polarity. Let's go plus, minus. This is random, plus, minus. This one can go down, whatever. I'm going to observe that the only resistor that's going to have a current that's a bit weird is the 4 ohm one. And I'm going to find its current using KCL at this node. I'm going to call it I4 ohm, because why not? And I'm going to write a KCL equation. So going in is I1. I infinity is going that way. I4 ohm is going down. So entering is I1 equals I infinity plus I4 ohms. So therefore I4 is equal to I1 minus I infinity. Fantastic. Okay, now I can write my two mesh equations. Mesh equations, I just go around the loop. The first sign I see is the sign in the equation. And otherwise, I'm writing voltages. So that's current times resistance. Or if I see a voltage source, I just write the number. Fantastic. So to be super clear about that, the first one I see is going to be this minus 40, because I've seen the minus sign first. So minus 40. Next one is this one. Plus, and Ohm's law is V equals IR. There's R. There's I. R and I. Next, I see the 4 ohm. That has current I1 minus I infinity. I1 minus I infinity times 4. And then I see the minus 10. And that's equal to 0. Equation 1. Equation 2, we've got 10. Now I see the minus sign. I'm going around this way. So now I see the minus sign of the 4. And this is the same current again, I1 minus I infinity. Notice I didn't like flip around the currents or do anything funny like that. I see minus sign, I write minus sign. I don't want to think that hard. Plus 8 I infinity. That's equal to 0. Okay, so this is now, right, this is a system of linear equations. Hopefully we're a little bit familiar with this. I might skip straight to the solutions if that's okay. Are we comfortable with solving a simultaneous equation? No one wants to watch me do that. Great, because I don't really want to do it. I kind of hate doing them. I won't lie, I plugged this into Wolfram Alpha. I can't be bothered. You unfortunately have to do it, but I don't anymore because I don't take in this course and you kind of stop doing this stuff after first year. Anyway, actually that's a lie. 2134, you have to do this a lot. Ooh, I know, exciting. What a great course. Everyone loves that course. Okay. So we get I1 equals 3.57 amps, hopefully, unless I tapped into Wolfram Alpha wrong. And I infinity is equal to 0.36 amps. At this point, you have to take a step back and go, why on earth did I do this? Right? I've just done all this maths. The question was like 5 minutes ago. Why did I do this? I did this because I wanted to plug it into this formula. So that means there's actually one more thing to do, which is calculate tau. Remember, again, tau is our time constant. And it depends on the resistance in our circuits. So once again, we want the resistance as seen from where the inductor is, which is those 2 pins. So in general, I can use any of method 1, 2, or 3 for Thevenin. Because we only have independent sources, I'll use method 1. Beautiful. So I'll whack off the 2 independent sources. That means they're replaced with short circuits. Pretty cool point. That's right, isn't it? Yeah. Because voltage equals 0, that's a short circuit. And we get a circuit that looks like this. There's our 2 ohm. There's our 8 ohm. There's our 4 ohm. And there are our terminals for the inductor, A, B, 4, 2. So we want the equivalent resistance. We can see 2 and 4 in parallel, and then 8 is in series with that. So R is equal to 8 plus, I'm just going to write like this, 1 over, I know there's like some fancy formula where if they're like the same, you can multiply them on the top or something, but I don't remember that one. I just remember this. At this point, you get your calculator and you type it in, right? And you get 9.33333333. Great. So now we can calculate our tau, which is L over R, which is 9 point, that number, 1,000,000, divided by 5, which is 8? No, 3. I can't read my own handwriting. Oh my god, dude. Yeah, you're right. Holy moly. This is not a damn. Thank goodness you guys are here. Firstly, because it'd be really unfun for me, but mostly because yeah, damn. That makes more sense why I got 8. I was like, how do I wait? No, it doesn't. What did I write? Can someone type this into their calculator? Oh, I did this wrong in my notes. Okay. This is like a half, right? What's this number? 0.539. I'm going for 0.53 because I didn't hear the rest of it, and that's fine. That's close enough. Probably not for you guys. You should probably leave a few more decimals, at least in safety. You don't really want to lose a mark because of like your calculator error. They shouldn't take one off, but you don't want to risk that sort of thing. Particularly because you can't really dispute your final. Anyway, so now once again, I think, why did I do this? So I have I0, I have I infinity, and I have tau. So now I can finally write, okay, great. So I of t, equal to, so I of t0 was 4, I think. 4 plus, we had, what is this one? Oh, it was I infinity first. Good grief. I'm making a lot of mistakes today, everyone. My sincerest apologies to all of you. So I infinity was 0.36. And then this one was 4 minus 0.36. So I'm just substituting straight into our general formula. And I'm going to leave this as t minus t0 for now, divided by our tau, which is 0.53. Now, one trick here is that our t0 is no longer 0. So I can't just write t over. T0 is 4, because that's when the transient period has begun. So for this equation, I have to write this 0.36 plus, and I'm going to do the subtraction now, which I hopefully didn't mess up. I think I can do this one. 3.64, right? Okay. E to the minus t minus, it was 4, because that was t0 over 0.53. And that's I of t for 4 onwards. I'll do the last part and then I'll ask some questions, or I won't ask questions. You will ask questions if you want. And then you can do it. No, I'm joking. Final part is determining V of R for t is greater than or equal to 4. This is a common thing for them to do, right? You've spent all this time working with like the inductor currents, or maybe it could be the capacitor voltage, and now they're like, oh, find a different circuit element. How exciting. That's crazy. Usually it's not very hard because it's the end of a question and they don't really want to like make you do something nasty. You'll notice for this one, they're asking us to find this voltage, and we know it's current. So we can use Ohm's law. It's really crazy. So yeah, just to be super clear about that, VR is going to be equal to I of t times 8, because our current is going that way, and that's like the entirety of it. Say that in general, this could be a lot harder, right? They could have asked for like this voltage. If they asked for that voltage, that'd be kind of mean. You'd have to do like a full like mesh analysis, right, with your current, and that'd be really grotty. So, but they didn't do that, which is nice. They just asked for this one. So this one's super easy. We just multiply our final result by 8. The V of R equals to 8 times I of t, which is equal to 8 times that whole expression, whatever that's going to be. I don't like multiplication or addition. Actually, addition's fine. All right. Okay, so that's the first 2 questions. I moved really quickly. Are we happy? Thoughts, queries, anything? I might pause for like 1 millisecond. Yeah, what's up? Sorry. Wonder what I can do. That's a good point. Yeah, maybe.
If you registered on the form, I'll send a PDF copy to everyone.
Here it is, a form for us.
I registered, but I didn't get any email.
Yeah, I didn't know.
I'll send it through now.
We'll leave this to our ELSOC representative will handle administrative things. There's a reason I stopped doing ELSOC stuff, and it's because I can't be asked to do that sort of thing. Yeah, what's your question? Yeah. Yeah. Okay, yeah. So that's a good question. The thing to recognize is as soon as you've calculated that current, hang on, let me just think for 1 millisecond. I think that would be too mean. I won't lie. I think if it had to be complicated, that would be too hard. So I don't think you'll get that. If you do, sorry. But I'm pretty sure what you would have to do is, because you know this current, the best way to represent you knowing a current is writing a current source. So you would probably put a current source here with IFT, and then that's an element you can treat normally in your circuits, if you know what I mean. Yeah. Like at that point, you have a circuit you can solve normally with all your normal analysis, is my point. Yeah. Yeah. I actually have never seen one. So yes, that's why I'm not 1,000,000% confident as to how you do it either, because I've never actually seen one. So yeah. I think this is much more normal. Series resistance is pretty. Are we happy? Any other questions? Otherwise, I'll do question 3 after I collect myself. Oh, want to ask me if I want anything for my birthday. All right, I'm making okay time. So, how is the pace? Is the pace too fast? Yes, too fast. Okay, I will chill out a bit. I'm covering enough content, so I'll chill out. Okay, sure. I'll slow down a little bit. So far, hopefully those two, like those were just both DC questions. Hopefully we've seen them enough as well that it's not the end of the world. Oh, that's not fun to watch. All right. By the way, I saw some people taking pictures. Does anyone else need a picture of anything before I just keep on moving? All good? Happy? You've lost your opportunity. Okay. All right, let's do question 3. So this is obviously an op-amp question. We've got the scary triangles. The first point I'm gonna make, because this confused me, is I was like, oh, is my pen broken? Dude. Fuck. Can we not do this? Come on, let's go. Oh, fuck off. No. Oh, let's not look at my tutoring student. True. All right, brief intermission while I fix my Apple Pencil. Oh, are we back? We're back. Okay, intermission over. Yep. Some of them have solutions, some of them don't. So yeah, but I will obviously present all the answers. So okay, the first thing that confused me was I was like, where are my voltage sources? I don't see voltage sources. This is bizarre. How do I handle this? You do have voltage sources. They've just drawn them a bit weirdly. The voltage sources would go like here, right? Oh God, can I just draw a circle? The voltage sources would go here and here. So in theory, right, that could be between any two nodes, but these do happen to be between ground and some other source. So that's okay. That makes our lives a little bit easier. The other thing to note about this question is we have no numbers. We are doing a purely like kind of theory analysis. That's fine. We can do that. Nothing we can't handle. Gonna make another comment for op amps. In my opinion, like I know at one point he like presents you with a page of like 8 op amp configurations. It can help to know a few. You probably don't need to know all of them, particularly like the hard ones that like have lots of stuff in them. But I would say the following ones are good to know, partly because they're kind of easy to remember because they're kind of simple, and also they come up a lot. The first one is this. Oh, I drew it wrong already. The first one is this one. This is our voltage follower or buffer. V out equals V in. Fantastic. So you want to know the configuration and what the equation is. There you go, voltage follower. Next one I'm going to write is the inverting amplifier. Looks like this. The out, the in. I call this RF. I'm going to call this R1. This one follows the equation V out equals minus RF over R1. So this one is inverting, times V in. Oops. So this one inverting because our input goes to the inverting pin of the op amp, negative pin, inverting pin. And you can also see it flips over our voltage. So our voltage goes in and comes out with 90 degrees phase, 180 degrees phase shift, or like inverted, however you want to think about it. Hopefully seen this in lab. Yes, sorry, this is grounds. Yep. Oh, another comment I'll make about this question. These grounds are connected together. Every time you see a ground label, it's implied that they're all the same grounds. Yeah, some people get confused about that. And then we've got non-inverting is the other one I think that you should know, because once again, it's kind of simple. And that looks like this. This one obeys V out is equal to 1 plus RF on R1 V in. So V out, I mean, this one is non-inverting because our V in goes to the non-inverting terminal, and our output does not have a minus sign out the front of it. It's just the same sign as the input. So yeah, I think you should memorize these three. I'll be real. You should memorize these three. It's really not that much to memorize. You see people studying med, you know how much shit they have to memorize? You can memorize this. Yeah. Oh, sorry. Yeah, I can hold here for a second. Yeah. Oh, yeah. So yeah, I'm gonna solve this circuit now anyway. Okay, so in spite of that, I can identify that this first one is an inverting amplifier because our plus pin is grounded and our minus pin has our input at it. So straight away, I can just go, if I know my equations, okay, let's call this node Vx. Vx is equal to V1 times, I'll draw it the same way I wrote the other one, is equal to minus R2 over R1 V1. The alternative, right, was doing a nodal equation, other shit like that. But now I can just be like, oh, great, I know that voltage because I remember my formula and I identified that this op amp is that. Okay. The next one, I think in theory is a summing amplifier, but I don't remember that one because that one's got more than 2 resistors in it, and that's too complicated for me. So we will just do the full nodal at this one. So you can always solve op amp questions by doing nodal analysis. The critical point, though, is you can only do nodal at the op amp input nodes, because our 2 op amp golden rules are V plus equals V minus, and I plus equals I minus equals 0. So those are those currents. This golden rule means that nodal at these nodes is really easy because we don't have to deal with that op amp input current. I'll contrast that to nodal at, for example, this node, where we could probably know this current and this current, but the output current of the op amp is not necessarily 0. It could be anything. It's also not like meant to be 0. It's not like a non-ideality or anything. It could be anything. So we can't really do nodal at this node, but we can do nodal at the op amp input nodes. So let's do that. Let's do nodal at this node here. So I'm going to redraw my circuit down below, or I'm actually just going to, no, I'll redraw the whole circuit. So we've got V plus R1 minus plus. I'm just going to draw it slightly. It might look a bit different, but it's the same circuit. R3. I think this was R4. Was this R4? Thank you. Thanks so much. R5, R4. And this is where V2 was going. Oh, I lied. Sorry. It is R4, but it's connected like that. Okay. So as before, we know this voltage, that's Vx. And we had Vx was equal to minus R2 on R1 V1. And then let's deal with this node here. So this node I'm going to call V minus, and this one's V out. I'm going to call right VO. All right, so let's do a KCL equation of V minus. So for that, we're going to have to decide on current directions and polarities. So I'm just going to do this, yeah, kind of randomly. Plus, minus, therefore going into the plus terminal, going to the right. Plus, minus, therefore going that way. Plus, minus, therefore going that way. Doesn't matter how I did that. We're happy with that. Does not matter. I just picked some random directions. I mean, I kind of always do it like that, but like it doesn't matter. So my mind just, I'm superstitious. Anyway, okay. So they're all going in. So they're just going to be on the one side of the equation. So the first current, that R31, Vx minus V minus on R3. And to be super explicit, it's this order because Vx is at the positive terminal and V minus is at the minus terminal. So when I'm writing these equations, I literally go, okay, Vx is plus, therefore on plus side. V minus is minus, therefore on minus side. Yeah. V minus is 0. Yeah. Yeah. I was going to say that in a second, but if we recall our golden rules, once again, we have V plus equals V minus. My pen is not liking this. Because V plus is at ground and 0 volts, you're right. V minus is actually 0. But I'm going to write it explicitly with all the voltages, and then we'll get rid of the ones that are actually gone. So V plus minus V minus over R3 is going in. Also going in is V2 minus V minus over R4. And also entering is V0 minus V minus over R5. And there's nothing leaving, so that's equal to 0. The observation was correct because I'm adding because I have said they're all going into that node. It doesn't matter. If I did this round the other way, I may as well show you briefly. Let's say I had determined, I'm going to do some red, that current's actually that way. This would be the same, but I would say equals, now the positive side has V minus. So I'll go V minus minus V0 over R5. These equations are actually the same. They're off by a minus sign, but I've also put it on the other side. So if I bring it to the other side, there's a lot of this side, that side. But my point is, if I bring that over there, I'll get the same thing. Doesn't matter. Okay, so yeah, by golden rule, wow, V plus equals V minus. That's amazing. What a miracle. Therefore, therefore V minus equals 0. So that's great. I can just get rid of them all. So my question is now this. I've got my pen. No, don't do this. I only get a new iPad, except I only use it for this. So like, why would I? Plus V0 over R5. Maybe ELSOC can buy me a new iPad. No, they can't do that. Maybe they can with the amount of money getting from this event. Anyway, V plus yada, yada, yada. Cool. So I want V0. So let's put V0 on its own. V0 over R5 is equal to, I'm just subtracting the other two, minus V2 on R4 minus Vx on R3. This is now just algebra from here because I already know that Vx is equal to minus, I think it was R2 over R1. Yep, R2 over R1, V1. Let's multiply out R5. V0 is equal to minus R5 on R4, V2, minus R5 on R3, Vx. And final thing is to plug that in. We get V0 is equal to minus R5 on R4, V2. And now I need to multiply two negative numbers together, which gives me a positive number. Yay. R5, R2 over R3, R1, V1. Okay, return to the question briefly. What was the question asking me? Make sure I've done it. What is V0 equals A1, V1 minus A2, V2. Okay, have we done that? Looks like we have. The signs indeed are going to be like that. So we've got, I'm going to write them in numerical order because that makes me feel better about it. R1, R3, V1 minus R5 over R4, V2. So you can see that this is indeed the form, and writing this would probably be sufficient, but I might also just write A1 equals R2 over R5. Sorry, R2, R5, R1, R3, A2 equals R5 over R4. And I've given that a positive sign because the question had minus A2. So that's done. Are we happy with that? It got a little bit messy, but it's kind of just algebra, right? So comfortable? I'm actually going great for time. So yeah, any questions? We'll take a brief pause. I see people writing down hurriedly. So yeah. Yeah. The V minus went away. V minus went away because of the golden rule, V plus equals V minus. That's applying to this op amp, and you'll notice that V plus is 0 volts because it's connected to ground. That's the only reason. If that had a different, if that was like some voltage source, 5 volts, then I wouldn't be able to get rid of V minus. V minus would be 5 volts now. So yeah. Any questions online, actually? I should know. I'm just so good at explaining things. I'm gonna get myself ready for the next one, but I'm still gonna take like 20 seconds. So yeah. All right, this is gonna be juicy. Also, it's got the answer as well. That's good. That helps. Yeah.
It's just gonna redraw it.
Oh yeah, sure. Do you want to just sit here for a bit? Here's the circuit. Yeah. That's a good point. This would be a very boring question in DC, right? Because yeah, exactly. So this would be a very, very interesting question. You could be asked this, but you have like a DC source. I should do this on my, what am I doing? Oh, my iPad turned off. No. You still here? Okay. I think you could be asked this with a DC source like here, maybe. Then you have to do superposition, which would be really sad because superposition is not much fun. So probably have to do that. But you're right. The thing you probably wouldn't have to do is transient analysis. I think that would be too nasty for these op-amp. I mean, I guess you could do it like with a switch, but that would be a bit grotty. Like, surely not. Also pretty unusual. Like, really? Are we really doing that? Come on, Felipe.
Sure.
What are those? The general expressions. Oh, like it's a differentiator, things like that. Maybe, right? I mean, okay. I'm looking at this. I don't spot any topologies I recognize, right? This has feedback over like 2 op-amps. So that's not any of our standard configurations. We have to do, I'll start this in a second, but we'll have to do nodal over the whole thing. If you saw a differentiator and it was in DC, yeah, you could do differentiator, but a differentiator is not a differentiator. Well, it's still a differentiator, but it has a different form in AC. Like, we don't treat it as a differentiator. I think I don't have an example. I kind of have an example of that here. Like, I'll show you what it looks like, but all right, I'm gonna start now. Okay. Oh, I've cut it off. Apologies. There we go. All right. I was going to need that as well. I was about to run into some trouble. Okay, all right, here we go. So first thing I'm going to do in my head is try and classify this. So as I've kind of discussed a little bit just then, we have an AC source. There's going to be an AC steady state question. Not DC, so it's not DC. We have capacitors as well, fantastic. No switches, so it's not a transient question. That would be really disgusting with op amps. It could be done, actually probably wouldn't be that bad, right? You just do the normal things with op amps and normal things with transients, but hopefully we're not doing that. Anyway, okay, so we're in phasor domain. So let's write impedances. We can identify our frequency is 10 to the 3. That's our omega is 10 to the 3. I'll note that omega is 2 pi f. If they tell you frequency is 3 kilohertz, and that is not your omega, you need to multiply by 2 pi. In this case, they're just giving it to us directly though. So that's great. So I'm going to write that directly here as a phasor. Amplitude is 12 degrees, angle is minus 60. And that omega is only used to calculate the impedances of the 2 capacitors. So we may recall that the impedance of a capacitor, is this given in the formula sheet? Oh, I can't be bothered to check. It's a long way away. Is ZC is equal to, that's the 1 over j omega c, which is the same as minus j over omega c. Yeah. Understandable. This is by complex numbers, you know, you times them together, you get weird shit. Yeah. Actually, I'll be more explicit. This is by doing this. J omega c times j over j equals j over j squared omega c. J squared is minus 1. So therefore, minus j over omega c. Okay. Cool. So let's do that. Micro, that's a mu, that's micro, it's 10 to the minus 6. Yes, it is. Oh my God. So I'm just going to write them directly onto this circuit. Actually, no, I'm going to redraw the circuit. Give me 1 second. So this was 12 angle minus 60. We had a series capacitor. We had the first, oh wait, I've got a picture on my little book. My first op amp. It's going to grounds. I'm going to draw all the grounds like this because it's more concise. They are all connected together. Not that it like really matters too much, but yeah. That's plus. That's grounded as well. And we've got another capacitor. Oh, these are all capacitors. Sorry, hope my drawings are not too terrible. There's 50K. There's 20K. Okay, only other thing to do is write the impedances. So this one was 0.1 microfarads, which is going to become minus J over, I think it was 10 to the 3 omega times 0.1 times 10 to the minus 6. According to my calculations, this is minus 10,000 J. Just by plugging it into the calculator. Oh, at this point, I'm going to make another point. A complex number calculator helps a lot. Buy a complex number calculator. You're buying marks, like not even joking. You will actually like increase your final grade by like 50%. Like it's a bit pay to win, whatever. You just spend the $50, okay? Everything else is on hex anyway, so like you probably didn't even buy the textbook, right? So like may as well spend anything. Okay, the other one is 0.2 mu f. I mean microfarads. What the fuck? The other one's 0.2 microfarads. That's 2 times the other one, so I know that's going to be minus 20,000. You can also type that directly in, right? That's minus J over 10 to the 3 times 0.2. Oh, wait. It's 1 over. Holy shit. Wow. Damn. Okay. Yikes. Okay. Yeah. Minus 5,000 J. Oh, my God. Okay. Don't do that. Just write the impedance. Wow. Okay. Look, I had design proficiency G today, okay? Get off my back. Anyway, okay. So now, yeah, I don't recognize the structure. We're just going to do nodal. Once again, the only nodes we can do nodal at are this one and this one. We cannot do nodal at the output nodes for the argument I made before. We don't know their currents. You can't write a KCL equation. So I'm going to assign everything a polarity now. Again, this is going to be basically random. Today I just went left to right. I'm going to give them all arrows because it helps me remember what's happening. The only caveat is the arrow must agree with the plus and minus. The arrow must be entering the positive terminal of a resistor because resistors dissipate power. You may remember passive sign convention from like week 1 or something. That was a long time ago though, so fair enough if you don't. Okay, I'm going to call this what? I'm going to call this V1. I'm going to call this V2. And let's do it. Okay, so at V1, entering is 12 angle 60 minus V1 divided by minus 10,000 J. Oh, you're right. God, minus 60. Leading is the other two, so they're equal to V1 minus. Oh, I need to label this as well. Even though I can't use it, I'm still going to label it. I can use it. I just can't write a KCL equation at that point. Over 20K, and the other current is that other 50K currents, which is going to be the plus terminal is at V1 again, and we're at V0 for the negative terminal 50K. Right, that's nodal equation 1. That's V2. We have nodal equation 2. Only 2 currents. Entering is V3 minus V2 over, I think it was 10K. Was right, 10K. And that's leaving as well, which is going to be equal to V2 minus V0 over negative 5,000 J. Okay. So far I've implicitly applied golden rule 2, the one about the currents, by writing these equations. Let's explicitly apply the other golden rule, which is V plus equals V minus, which means that V1 and V2 are both 0 because they are both going to be the same as their respective plus terminals, which are at grounds. There's grounds. They're at grounds. 0 volts. Beautiful. So therefore, our equations are actually 12 angle 60 degrees over minus 10,000 J is equal to minus V3 over 20K, minus V0 over 50K. And V2 was the one that was 0, so V3 over 10K is equal to, yep, minus V0 over minus 5,000 J. Okay, I'll do I'll now solve this up to the point where you have to put into a calculator, and then I'll let you do that yourself because I actually don't own a complex number calculator. I know I told you to buy one, but I should have one. Yeah, what's up? Of course, my apologies. Sorry. Okay, I might just go back over what I did just then, just quickly, or not quickly. I am so sorry. Okay, so the point here, right? Two nodes we need to do KCL at. That one. At the first node, entering, we have this current. Leaving, we've got this current and this current. So I'll write a little current equation for each of them. The first one will look like this. It's always the positive terminal minus the negative terminal divided by that. That's what happens. Coronavirus still exists, by the way. Just let it be known. Equals. Yeah, actually, they do have vaccines over in the medical center. Yeah. Okay. Anyway, I'll confuse myself now. Okay. So yeah, that's one current going in. The other currents I write the same way. Starting node minus. Oh no, I wanted this pen. Starting node minus finishing node, wherever that is, divided by the resistance. That's this term. That's this term. Sorry, can we just quiet down a little bit? Thank you. Likewise, at V2, I do exactly the same thing. This current's entering, this one's leaving. So I will subtract the higher current from the lower currents. Or the other way around, I'll subtract the lower current from the higher currents. Like I just look, there's plus, there's minus. Did them together. Here I applied this rule, which implied that V2 equals 0 and V1 equals 0. Because they're both connected to 0 volts. Or they're both the same as this node, which is connected to 0 volts. Yeah. So from here, we have two equations with two unknowns. Fantastic. We can write them all out. So what I'm going to do is, yeah, I'll get to a point where V0 equals long expression, and I'll leave that to you for you to put into your calculator. I do have the answer as well, so we can confirm that you guys have done that correctly and I haven't made a mistake. Okay, so this equation looks like an easy one to do substitution. So V3, I'm just going to multiply the 10K out, equals minus, I'll get rid of the minus signs as well because they're top and bottom. 10K times V0 over 5,000J. I'm going to observe that I can cancel off the two Ks, if that makes sense. We've got a K at the top and the bottom one's 5,000, which is the same as 5K. This is 10 over 5J V0, which is a half. No, it's 2. Oh my God, which is, holy shit, which is 2 over J V0. There we go. And I can do the same thing to get the J on the top, which I might as well do now. Minus 2J V0. Yes, hang on. J squared is minus 1. Yep, cool. Okay, that can be substituted into this equation. We'll have 12 angle minus 60 divided by minus 10,000. Sorry, got to keep scrolling. Equals minus. Oh, this was V3. Just remind myself, this was V3. So minus that thing, which is going to give me a plus over 20K minus V0 over 50K. Is going to be equal to V0 2J over, I'm just factorizing 20K minus 1 over 50K. Therefore, V0 is equal to. Okay, you could multiply by that, but we want to isolate V0, right? So I'm not going to drag things over to the same side as V0. I'm going to do the opposite. I'm going to drag them away. So I'm going to write the most disgusting fraction you've ever seen in your life. Now, I'm pretty sure you can put that into your complex number calculator. So that's why you should have one, because if you can't do that, now you have to keep going and you have to like write the complex part on its own and write the imaginary part on its own, and it will take you 10 minutes and you'll get it wrong as well. So at this point, seriously, just, yeah, you spend $50 and you win. So yeah, literally $50, 50 marks. And that should give you the answer, which according to the question was. Only other point I'm going to make, you'll notice that this is no longer a phasor. Let's say we got the answer 11.767 angle minus 71. They just go in there. So yeah. The only other thing you may have to be aware of is, yeah, this could give you a number in rectangular form, like some sort of like, I don't know, 55 plus 11J or something. You would need to go into phasor form. There are just formulas for that. The formulas are basically, like you think of it like a vector. Calculator can do it as well. You just press the button, right? Yeah, okay. Yeah, okay. Okay, so don't even worry about this. Yeah, what's up? Sorry, can we just quiet down a little bit? Sorry, I won't be able to hear. Yeah, what's up? Yeah, if you're given, okay, that's a good point. Notice how they've asked for V0 of t. That tells us they want time domain because they've asked for a function of time. So that means, yeah, we'll have to go back to time domain. So yeah, so basically once you've got your rectangular form, you can press the button, your complex calculator, damn, to go into phasor domain. Once you're in phasor domain, you can write it like this, just like that. Notice the frequency is the same. And we've used cosine because they used cosine in the question. If this had been sine, you would use sine. It doesn't matter, right? There's just a small phase difference between them, which like you be consistent. If they give you cosine, you stick with cosine. Look, kind of hard to say, right? I mean, I don't know. I don't ever mark these, but you may as well give as many as you can, to be honest. I mean, 3 is probably definitely fine, I would say. Yeah. I don't think we care so much about rounding in this course. This isn't like physics where they're like, you must propagate your significant figures. Like, we don't really care about that. Yeah. Because the other thing, right, is in theory you should do one calculation so you don't propagate errors through your working. If you like round off earlier and then reuse a round of results, that will be more wrong. But they kind of don't really want to punish you for that. So, but you still should do it in one go if you can. Yeah. That is the best practice, yeah. I mean, doing this does increase your chance of making a mistake plugging into your calculator, which is probably like a big source of error, to be honest. Like, it's really hard. So maybe you can do something like calculate this one and then use like the answer button or something. Yeah, something like that, right? Like, there's calculator strategies. But yeah, that was always too fancy for me. But yeah, you can do that. I know. Yeah, it's kind of crazy. If you're able to do that, then good stuff. Yeah. All right. Any other questions? Otherwise, there's only 2 more questions, I think. Yeah. Why don't we take another minute or something? How many questions do I have? Let me just check. Okay. Okay. Well, yeah, we definitely got time. So let's take 5 minutes. I also need to go to the bathroom. So I'll be right back.
So community has their own like you know? Yeah. Guys, why is even I go, you should get.
Like there's
Wait, I don't think they can use any. Divided by.
Good. Think twice more, huh? We'll have access to
We'll start in like 2 minutes. Anything anyone wants to ask? Discussion points, anything? Yeah, what's up?
I think they were enough to
Just like really readable.
Grab some drinks. Yeah, no side.
Any other questions before we resume? Second as a no. No one said anything online in a while. All right, shall we do question 5? The answer is yes, we shall, because we've got time. I sped everything through quickly enough such that no one understood it and that we can get up to question 5, so let's do it. We're going to spend a lot more time on the next two because these are completely new, right? The other ones I think in theory you've seen before a little bit, but these ones are completely new. Yeah. I do apologize for the speed. Sometimes I don't know. All I've consumed today is a coffee and I don't know, a bit of food. So, oh, you guys are so sweet. No worries. I'm gonna take 1 more minute. I lied. Let's go. All right. It's time to begin the next question. Here it is. For the circuit in figure 5, which is this circuit, find the voltage V0 of T. So here's V0 of T. There it is. It's over there. They've given us a polarity, which is nice. Be very hard. Well, it wouldn't. You just would, I don't know, have to guess otherwise or something. Or they couldn't possibly ask you to do it otherwise, really. So I've got 2 sources, one of which is AC with omega equals 3. The other one is, oh, this isn't providing power. I didn't have my power supply on. The other one, power supply, my charger. The other one is DC, right? So this is a 12-volt DC source. I'm going to write that as omega equals 0 for the purposes of this. Yeah, that's a good response. That's a good point. I don't think you would be given a transient response plus an AC steady state question. I think they will be both steady state. I mean, they probably kind of could give you a transient response plus no, I don't think they really could. I think that'd be a bit weird. No, I think you can be pretty certain you will not see them. It would be mean, it'd be weird. Well, there's no switch, right? So there's no transient response. Yeah. All right, okay, so we'll have to do superposition. We'll have to do the question twice, unfortunately, but hopefully it'll be simpler. Neither equation. We mind quieting down, everybody? Yes. Yeah, sure. We can do whatever we'd like to do. I probably will do mesh. Yeah, mesh is a good suggestion because 2 loops, many nodes, right? Node. Too many nodes. But mesh, like the sound of mesh. We'll do mesh. Well, we have to do superposition, but within every superposition, we will do mesh. Unless the circuit's sufficiently simple, we don't have to worry, but we'll find out. Okay, so we have to do superposition because we have different frequency sources. Y'all are chattering so much. Shh. Sorry, guys. Just yeah, we have to do superposition. The reason for that is the impedances will change with different frequencies, so we can't possibly do them at the same time. That's basically the reason. If we're trying to do everything at once, we would be faced with the choice of what impedance do we give this, what impedance do we give this, because these impedances are j omega L and minus j over omega C. And we'd be faced with the choice of which omega do we use? Do we use our omega equals 3, or do we, I mean, this is DC, so it doesn't even make much sense, but do we use that omega? And the answer is we use both, we do superposition. Let's start with the DC source because DC is kind of nice. So this is DC steady state, so we can replace our reactive components, that is the capacitor and the inductor, with their respective steady state counterparts. So for an inductor, that's a wire. Another way to understand that is if we put this omega equals 0 in there, we'll get an impedance of 0. So great, that's just a wire. Likewise for the capacitor, that's going to be an open circuit. Another way to think about that is if we put omega equals 0 into there, we'll get 1 over 0, which I mean is undefined. It's like it's going to infinity, right? It's a big number, or it's not a number. But yeah. So that will be an open circuit. That one will be a short circuit. And also we turn this source off. Turning that source off means replacing with a short circuit. So our circuit, once we've done all of that, I've said the word circuit a million times, looks like this. We've got our 2 ohm. I've just drawn it over here instead of horizontally because I actually don't know why. I just kind of did that. Minus plus, straight line, 0, 3, 2. So you can see this circuit is now actually like very straightforward. So we probably don't even have to do a mesh equation anymore. We can probably just use voltage division. So I reckon we'll do that. Yeah, what's up? So when we're doing superposition, we get to separate out the contributions. Yeah. Oh, okay. This is a supportive environment. That's quite funny. Okay. Yeah, it's recorded. That's gone down forever. Okay, anyway. To be fair, I don't know how much they can hear online. The microphone's here, so probably nothing. Anyway, yeah, so superposition, we get to separate out our sources. So you're right, like in the overall circuit, there's a contribution from both sources, but we can treat them separately and add them together at the end. So let's do voltage division. Yeehaw. That looks like this. This is just the formula. 12 times 3 divided by 3 plus 2. This is the one we care about, the 3 divided by the equivalent resistance of the entire circuit, which is just the sum of them both. So this is 12 times 3 over 5, which is 36 over 5, which is, I don't know, like 3.2, did you say? 7, holy shit, 7.2. Yeah, cool. 7.2 volts. Fantastic. Okay, so that was nice and easy. All right, now, unfortunately for the AC one, we will not be able to really eliminate anything because none of the components are just going to go away magically, except for our source, but that's the whole point. So, all right, so I'll draw the circuit again with all the AC components. We've got our volt source. I'm going to write this in phasor form now, so that's going to be 5 angle 45. Someone said, I think this is sine, so should it be different phase? Not necessarily. I can just work in sines for this question. That's fine. The problem is if we have both a sine source and a cosine source with the same frequency, then because we can't do, like we could do superposition, but we can also incorporate them together. And in that case, we want to make sure they agree on which sine or cosine they're using. You can do it. I mean, it won't make any difference because you'll get a V of t equals something sine 3t minus 45. That's still correct, right? but you're right. I mean, I guess, yeah, converting it over to cosine is fine as well. So look, a lot of this course is doing things that you feel comfortable with and you're happy to do all the time. So if you feel happier converting to cosine first, do that, 100%. Yes, definitely still correct. Like you're still going to get an equivalent sinusoid function, right? Like you can just write it like this. So phases are always offset with respect to something. You might have seen this in the labs as well, right? You calculate the phase of your pure sine wave. It makes no sense because it's centered at 0. So it's like, what is it? A phase is always relative. So you can choose where to start your phase, but I guess the convention is cosine, so that's fine. If you feel more comfortable doing that, just do that. It's fine. Yeah, what's up? Yeah. Fucking no, dude. I think it's plus. Is it plus? It's plus. Oh, he said minus. No. Okay. All right. You know what we're gonna do? We're gonna look it up. I'm not even joking. We're gonna Google it. Where's my mouse gone? I've lost my mouse. All right. Shh. I'm going to Google it, and we will find out together. I swear to God, this is the one thing I don't know. Maybe there's a reason why I was sticking to sine. Convert. All right. Hang on. Oh, we can see my mouse now. All right. Hang on. I'll go to your course. The AC one, right? AC analysis 1. All right. Here we go. We're so close. No. Because there's a few things I don't remember, and this is one of them. So what is it? Sine. Okay, so I'm the authority of information. I will say. Wait 1 second while I think. So we have. Okay, hang on. So we have sine of 3t plus 45 degrees. The equivalent. Oh, you can't see this. Actually, you know what I'm going to do? So what's our first candidate? Oh, it's not plus. Oh, because I didn't add them together correctly. Okay, minus 45. Oh, what? Am I okay? Oh, this isn't radians. Hang on. All right, there we go. Okay, and now I've got to zoom out. How long have we got? Okay, I'm not wasting too much time. It's all right. Sorry, this is probably something I should have prepared before, but here we are. So, oh well. 360. There we go. And let's make this a little bit smaller. We'll go from -1 to 1. How beautiful. Okay, cool. Beautiful. All right. 45. Okay, they're the same. There we go. So x plus 45 is the same as cos minus 45. They will be different. Ready? It's definitely minus 90. Okay, we're comfortable. Thank you for those of you who said that already. I apologize for not believing you. I wanted to be, so we're all convinced. Let's be super, super clear. Oh, I'll have to share my screen again. Hang on. Oh. All right, okay, we good? There it is. All right, okay. Apologies for derailing. We're good. We're good. Fantastic. Okay, let's keep going. That being said, I'm not changing what I've done so far, so we're going to stick with science. I emphasize it does not matter that much. Let's continue with the question. Okay. Oh, I did those backwards. Whatever, doesn't matter. They're in series. Oh, it does matter. Okay, so this was 3 ohms plus minus V0. This one was 2 henries. This one was 2 ohms. Sorry, I'll stop flickering around in a second. 0.4 F. And 2 ohms. Okay, all right. So now we just proceed with our normal AC steady state analysis. So we're going to first write impedances for our two reactive elements. So for the capacitor, that is ZC is equal to minus J over omega C, which is minus J divided by omega was 3 times 0.4 farads. So this is going to be minus J over 1.2. And that's, yeah, ohms or something. Then for the inductor, it's very similar. ZL is J omega C. This one's just all in the numerator, no fractions. So this is J times 2 times 2, which is just 4J. Cool. They're giving us nice numbers. Now I reckon we do mesh. I like the idea of mesh. So can we use voltage divider? We kind of can, but I think you'll suggest, wait, just shh. We have, okay, every question we have heaps and heaps of options, right? I'll just speak for 1 second and then I'll call you. And every question we have heaps and heaps of options, right? Honestly, the best thing to do is the first thing that occurs to you. Because if you sit here and go, what is the best way to do this question? Oh, I'm not sure. You spend 5 minutes doing that, you freak out, you die, you know? So what you do instead, Felipe won't kill you, it's okay. Anyway, what you do instead is you honestly do the first thing that comes to mind. But it's good to be good at nodal and mesh because they will always work, right? They will always work unless you like have to use superposition, but otherwise they will always work. So you're right, a voltage division could work. The problem with that is you would need to like voltage divide this thing with respect to everything and then individually voltage divide over there because you've got these parallel branches. Like it's perfectly doable. If you want to do that, that's fine. But for me, that's not instinctive. I'm not going to do that. Yeah, what do you? Oh, you're right. What am I doing, dude? Omega is 3. Damn, because it's written here, right? Thank you. Wow. Having a good day. And that means this is 6. Okay. Okay, so yeah, I'm going to do mesh. The suggestion of voltage divide is perfectly fine. You can do that as well. But I'm going to do mesh. So I'll note that they probably should give you a polarity for the source. It doesn't matter that much though, so you can kind of assign it if they don't give you one, but they probably give you one. I'm doing this arbitrarily once again. I'm making sure V0 agrees with what they're giving me because I may as well make my life a bit easier. All right, here's one loop. There's the other loop. Once again, for the shared elements that are between the two loops, I'll have to figure out their current individually. I'll have to use KCL. So I'll do that here. I1 is entering that way. We've got I2 going out that way. Down here, we've got some other current. I'm going to call it I3. My KCL equation is entering is just I1 and leaving is I2 plus I3. Therefore, I3 is going to be I1 minus I2. Fabulous. That's very cool. Okay, so now we can continue with our mesh equation. So we'll start with I1. First sign I see, I'm going to go around this way. First sign I see is negative. That minus, so I'm going to write a negative sign, and I'm going to write 5 angle 45 degrees. I see a positive sign, plus 2 I1. I'm now at this element. I see a positive sign, plus I3 is I1 minus I2 times 2. And then plus the impedance of this capacitor times that current again. So plus I1 minus I2 times the capacitor impedance, which is minus J. I'm going to put this in brackets over 1.2. That's equal to 0. There you go. That's loop 1. Loop 1. Loop 2, I might have to scroll a little bit, or I'll try my best not to. Hang on. Let me just kind of shift all this up a little bit. Oop. Okay. So this loop, let's start here and go like that. First sign I see is negative, so I'm gonna write negative. I3 is the same as before. Notice I haven't like swapped the direction of I3 or anything like that. I've just seen a minus sign. That's how that's taken care of. I1 minus I2. Capacitor impedance again was minus J over 1.2. Once again, a minus sign times the same thing again. I minus I2 of 2. Next thing I see is the inductor, which has I2 going through it. And inductance is 6J. 2 times 6J. And the last thing is that same current going through 3 ohms. I could also write V0 here, but I might not do that just yet because it'll introduce a new variable. I can do that later. So now I have 2 simultaneous equations, 2 unknowns, perfectly solvable system. Let's do it. 1, 2. Once again, I'll just get to the point. You can type in your calculator and I'll let you do that. So my strategy basically is to get like something times I1 plus something times I2. So let's do that. I'll write the 545 degrees on its own. I'll move that to the other side, and we'll collect terms. We've got 2 plus another 2 from there, and then plus a minus j over 1.2. For I2, we've got minus 2 plus j over 1.2. I've just distributed that minus sign. Cool. Great. That's equation 1. Equation 2, it's going to be a little bit more complicated. So that's equation 1. Equation 2 will be, so I1 times j over 1.2, once again distributing the minus signs. Minus 2, that's it, plus I2 times, so minus sign times minus sign times minus sign is going to be a minus sign. I'll leave you to juggle the minus signs yourself, but that should be correct. Plus 2 plus 6j plus 3. Okay. I can do some simplification. 1, 5 root 45 equals I1 times 4 minus j of 1.2. And plus I2 is just the same. Can't change that much. 1.2. 2 can be simplified a bit better. 1, that was I1. J of 1.2 minus 2 plus I2 minus j over 1. Oh, we've got 2 sets of j, sorry. So 5 plus j, 6 minus 1 over 2, 1.2. So yeah, 2 simultaneous equations. Are we okay if I leave you guys to figure out the details of solving this? It's just like substitution, something like that, bit of maths. Oh, that's true. I don't have the final answers. Maybe I better do this. Actually, yeah, honestly, I might do that later though. I'll do it at the end. I might just move on for now, and yeah. Does it? Okay, all right. Well, okay. I'll keep moving then. So are we happy with that? Any other questions? Yeah, something like that. Yeah, should be fine. Yeah, sure. Something like that. Otherwise, I'll do the final question. Question 6. All good? Yeah. And then you? Yeah, what's... So this came from equation... Oh, yeah, that should be a +4. Oh, okay, sorry, that's my handwriting. That is indeed a +4. I had drawn the bracket badly. Sorry about that. I think, did you have a question? Was there another question somewhere? Do you have a question before? Okay, well, good, sorry. Anything else? Happy? All right, final question. The power question. Another comment I'll make about power is that AC power is one of those things that can kind of tape onto the end of another question. So it's very normal for them to have like a whole exercise about, oh, do this thing, do this next thing, and now find the power. It's actually quite a big question. So yeah, we should do this. Now. Sorry, we're getting there. Sorry. Oh, that is not it. Oh, that is it. Sorry. Okay. The variable resistor in the circuit of figure 6 is adjusted until it absorbs the maximum average power. Calculate the value of the load resistor R. Okay, so we know that this will occur. The first thing we need to identify, as soon as we see max average power, max anything like that, we think, okay, Thevenin, max power transfer. Next question is this DC or AC? Because that is basically the only thing that changes between DC and AC is max power transfer. That actually does change. We look at that circuit, we see we've got a phasor here and phasors everywhere. So this must be AC. I'll zoom in. This must be AC. So therefore, we have to use the AC version of max power transfer, which is that the Z load is the complex conjugate of the Thevenin impedance. And the power that delivers is this. B Thevenin squared over 8 R Thevenin. I think that's right. I mean, I'm pretty, that's right. An important thing to note is we're using R Thevenin, not Z Thevenin for P max. This is because an important result of AC power is that capacitors and inductors, so-called reactive elements, do not dissipate power on average. They only transfer power between each other. They do not heat up. I mean, in real life they do because they have imperfections, but in general they don't heat up. Yeah. Don't you mean, do we use this one? Is that what you mean? Sorry, you mean for the load? Yeah, so there's a small difference between whether they ask for a load resistance or a load impedance. So you're right. In this case, I think they've said a load resistor. So this one will just be the real part of the load of the, sorry, this will just be the real part. Oh no, that's, sorry, that's a lie. Oh my God. This will be, you're right. I think the absolute value, right? Yeah. That's a good point. Sorry, I forgot to mention that. So yeah, there's two caveats. The first caveat is power is only dissipated by resistive elements, which is why you have this. Or should that also be this one? I think that should also be this one. Sorry. I'm gonna check the data sheet. It actually does say in the formula sheet. Sorry, you've spooked my yeah, okay. So you can see it kind of tells you for a purely resistive load, we have this. For a complex load, we have this.
VTH forces, maximum powers of VTH for RTH. So in this case,
Yeah.
average odds divided by half. Is it like that?
I'm pretty sure it's still RL. I actually won't lie. This is a small point where I'm not 1,000,000% certain, actually, but we'll get there in a second. The first thing we can definitely do is calculate that load resistor, because we'll need, basically the principle is we need V Thevenin, Z Thevenin, and we'll find its absolute value, its magnitude, and that will give us the load resistor we're after for max power transfer. Cool, so we can do that. And yeah, once again, the principle is that, yeah, reactive elements do not dissipate power on average. They just transfer between each other. Resistors are the ones that actually heat up. They actually dissipate power to the atmosphere or the environment or your finger when you touch it. So calculate the value of the load resistor. This will just be calculating the equivalent impedance as seen here. So we only have one independent source. So we'll use method 1. Once again, this is Thevenin question. We can use any 3 methods. Let's use method 1. So I'll redraw the circuit ready to go, which will look like this. Capacitor, parallel resistor, and then 2 series. Yeah, okay. Inductor, resistor. After from these terminals here. So that's 8J, 20, and 30, and minus 10. So 8J, 20, 30. I think this is minus 10J. Is that right? Let me just check. Cool. Okay, great. Okay, so you see this a little bit. The first observation I'm going to make is this is in parallel with everything, right? This shares the same starting and ending node with this entire rest of the circuit. That's a little bit difficult to see, but that's true. So just keep that in mind. Next thing, these two are clearly in parallel, and they are in series with this. You can draw this loop that's in series. Let's start with combining the parallel ones. It'll be clearer if I do it that way. Always start with the simplification you can see first, because a simpler circuit is easy to look at anyway. We've got 1 over 30 plus 1 over minus 10J. This is a great candidate for the complex number calculator. Yeah, actually, can someone tell me what this is? This is, who has a complex number calculator? Thank you so much. Otherwise, I'll bust out my phone, but 3 minus 9J. That's okay. 3 minus 9J. Cool. Great. So that is the equivalent of this There it is. There's kind of the equivalent. That's now in series with the 20. So I'll add 20 to that and we'll end up with this circuit. So we've got the inductor. And now I'm going to write this as a series resistance. 23 minus 9J. And that's 8J. So once again, those two are in parallel. So we'll do this one more time. 1 over 23 minus 9J plus 1 over 8J. You can see, again, this is like a real chore by hands, but very easy for your calculator. Sorry, one more time if possible. I also actually can probably type it in myself. So if I beat you to it, I might just do it, but we'll see. How exciting. The small things in life, isn't it? I prefer a decimal. 2.777. 8.12J. Okay, thank you. Cool. I mean, fraction is probably better for your maths to like propagate fewer errors, but I'm going to use the number for now. Cool. Okay, so that is my Thevenin impedance. So to get the load, all I want is the absolute value of that, which again can be done with your calculator. If you don't have it, you would do this. Yes, you can do that. That's a number. For the maximum load, it is the absolute value. Yeah. So yeah, the distinction is, do you want a real load or a complex load? If your loads happen to be complex, you take the complex conjugate. If you must have a real load, the maximum occurs when that load is the absolute value of your impedance. So yeah, this is going to be some number. I might not worry about it. Actually, I'll write it down. It is, thank you, 8.58. Cool. Ohms. Fabulous. Great. Okay, part 2. Find the maximum average power received by R. Yeah? Sorry, what did you want me to do? Happy with this? Magnitude. This is the magnitude. All right, find the maximum average power received by R. I'm going to do the thing that will always work if you get confused, because I've gotten confused, which is I'm just going to find the Thevenin voltage. I'm going to find, am I? Hang on, let me just think. Sorry, let me just. Won't lie, I have actually forgotten how I incorporate this resistive load. I think it's just going to be the real part, the same as with this, but God. Okay, so in any event, I'll need VThevenin. So let's find VThevenin. And once we have VThevenin, at worst, I can just draw the circuit and calculate the power that way, which I might just do. So let's just do that. So once again, VThevenin is going to be open circuit here. If I draw the circuit in those conditions, it looks like this. Still got this capacitor here. Sorry, I'm going to have to do some scrolling. Capacitor, resistor, inductor. Okay, I should be able to remember that. Capacitor, that one, resistor, and then it's inductor, resistor. Like that, I believe. Sorry, I won't zoom so much. It was minus 10J. This was 8J. Did I? I did not. Thank you, though. 30 and 20. I misread this. 30. Oh, sorry. Series resistor. My bad. 30. This one was 20. And we want this. 10J. Sorry. 80 angle 15, and that one's 30. 80 angle, and it was minus 15. Okay, so for V7 here, once again, we'll just do more circuit analysis. The strategy, it's 80 ohms. Sorry, 80. This one's 30. This one's 80. I think strategy is probably mesh again. I really don't like mesh, but we're doing a lot of mesh. That's okay. Probably mesh again. And then once I know this current, I can just apply Ohm's law. I'll be real because I don't like source transformation. If you want to do that, do it. Like genuinely, do whatever occurs to you. That would definitely work. Source transformation actually is probably a good idea because then you would have current division between all of your. So that's actually a great idea. However, I'm not going to do it because my instincts tell me source transformation. I don't like it. So here we go. I don't like source transformation because in general, I don't like the circuit theorems. The circuit theorems are just extra things to think about when mesh and nodal will always work. So it's kind of like, I honestly don't use them unless I'm asked to use them, or I have to because of superposition. But some people really like source transformation. I know, like this genuinely, and it's fair. If it works for you, then do it. Like it's fine. I would argue, well, they're definitely more fundamental, right? So anyway, sorry. I got to stop yabbering. We got to finish this question. We've only got 10 minutes. And so do you. You also stop yabbering as well. Be quiet. Shh, 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 shh. Okay, let's do it. All right. I'm going to assign plus and minus like that. Plus minus, plus minus, plus minus, plus minus, plus minus. Yep, that's fine. Okay, this can be I1. I'll do this in a different color. There's I1. There's going to be I2. We'll have to do some nodal equation here. Let's write that current like that. We'll call it I3, I1, I2, I3. The KCL equation there will be I1 equals I2 plus I3. Therefore, I3 equals I1 minus I2. Let me be quiet, sorry. Shh. It's only a small room. You guys talk it's really loud. Okay, we'll go around. We'll start with the left-hand node. Minus 10J times I1. We hit the 30 ohm plus the current is I1 minus I2. I1 minus I2 times 30. And then plus 80 angle minus 15 degrees, because that's the voltage across that source. Fantastic. And that's equal to 0. Next loop is going to be minus 80 angle 15, minus 15 that is. We see the minus sign first. Sorry if that's a bit messy. That is a minus sign. Minus 30 times that current, which is I1 minus I2. Next, we hit, so we're going around this way. So we've now hit the 8 ohm inductor or the 8J inductor. That has a current of I2 plus 8J I2. We hit the 20 plus 20 I2. Yeah, minus 10. Oh, you're right, it is. Sorry, apologies. Because minus and then also another minus. That's my apologies. So to be super explicit, we see the minus sign first. Then we times by minus 10J I1. So you're right, that is going to become a plus 10. Okay, cool. All right, we'll crank this out quickly. So equation 1, equation 2, equation 1 is going to look like I1 times 10J plus 30 minus 30 I2 plus 80 angle minus 15 degrees equals 0. Equation 2, we'll have something similar. I'm going to put that equals 0. I'm going to put this on its own side because I like doing that. I1 minus 30, that's the only term for that one, plus I2. The 30 is now positive because the minus signs distribute. Plus 8J plus 20 equals 0. I'll do a full substitution. We'll get rid of I2. So I'm going to write I2 is equal to, I'm bringing this to the other side first, and I'm going to divide. So that's going to look like I1 10J plus 30 plus 80 angle minus 15 degrees divided by 30. Equation 2 equals 0. I've included that here. Oh, fuck, you're right. Sorry. I'm making so many mistakes today. Thank you for calling me out on that. You're right. Yeah, this is actually inequality. Cool. Okay, that's that. Once you have that, you plug that into I2. Once you have that, that'll go in there. And I'll rewrite this one as well for I1. I1 is equal to, I'll do the same thing again pretty much. So it's going to be I2 30 plus H, I'll make that 50. Minus 80 root 15 degrees, angle 15, angle minus 15 divided by 30. So then, yeah, I2 will go in there. And then you'll have to do a little bit more algebra. Okay, I'll do that explicitly. Let's do it. So I1 is equal to I1 times 10j plus 30 plus 80 root 15 degrees. We've only got a few minutes, so I might crank this out. What I will do instead is talk about how you do the last couple parts. My goal here was basically to get to the Thevenin equivalent circuit, which will look like this. V Thevenin, we know our Z Thevenin, and we also have our load. I was doing this because regardless of which form Pmax takes, you'll need V Thevenin. I'll be completely real. I can't remember what Pmax should be when you have a resistive load. You should check that. Okay, we're all going to check that. Happy? Check that. If you don't know though, like I don't know, my strategy was once you have this circuit, you can just calculate it. You know that it's going to be at this load. So you can just calculate the power through that resistor and that'll be fine. You know the total current through the circuit, you can use Ohm's law. Is that all good? Understood? No, I don't have it. Sorry. You can figure it out. I'll send it later. Anyway, the other thing I'm going to say in the final minutes, firstly, thank you for coming, everybody. But anyway, wait, just one more thing to say. Sorry, before we back up, I'll just talk about the last two questions. For the condition that achieves max power. Okay, this one looks nasty. They've asked you for max power for every element. The simplifying thing is that for the reactive components, there's no power loss. So for these two, 0. For this one, 0. So the only thing left to do is find power there, power there, power there. You know power through this one because you just calculated it. Then you probably need to do your other stuff like find the currents, find the voltage, that sort of thing. But you can probably reuse some of the analysis you did calculating this. Okay. And for this one, this is just ZL equals Z Thevenin star. The only other comment I'm going to make, one final thing, thank you for bearing with me, is as far as AC power is concerned, this formula is the most important one. This is your average AC power. So the important takeaway is it depends on the phase angle between voltage and current through an element. The reason reactive components have no power dissipation is because this phase angle is always 90 degrees. And cos of 90 is 0. For every other element, like for resistors, there's no phase angle, so you just get this. And for a source, in general, you don't know what it is. So you would have to find the voltage and the current individually and then find their phase angle. Are we happy with that? Any other questions today? What's up? This is instantaneous. This is instantaneous. So you'll see this as a function of time. Yeah. Anything else? All right, cool. Well, thank you very much for coming. Thank you, ELSOC organizing. Appreciate it. I'll send you all the stuff, whatever. Yeah, what's up? Family photo. Bye, goodbye.